Hello, and welcome to the third video in the P2 chapter Sequences and Series. On the screen is a starter question, an old exam question, to review arithmetic sequences. Just a quick reminder, for arithmetic sequences, we have the nth term is equal to the first term plus n minus 1 times the common difference, and the sum to n terms of n divided by 2 times 2 times the first term, plus n minus 1 times the common difference. And the first part of the question gives us the first term and the common difference. So I'll note that a is 30, d is minus 1.5, and the question is find the value of the 25th term, so n is going to be 25. Put all of this into our formula to find the 25th term. 25 minus 1 is 24. And put that on your calculator. You should get the answer minus 6. Quick check, does that make sense? We're starting at 30 and we're going down by 1.5. Yes, eventually we're going to hit negative numbers. So that looks about right. Part 2. The rth term of the sequence is 0. Find the value of r. So they're telling us the answer this time, and we need to find n. So a is still 30, d is still minus 1.5, and the rth term, which is 30 plus r minus 1 times minus 1.5, from the formula, that must equal 0. So the question is, what is r? We rearrange this and we can find out. And if we do that, minus 30 divided by minus 1.5 plus 1, I get the answer 21. Of course, you can check this by putting that answer back into the formula and making sure that the term is 0. Final part, the sum. Here we've got the formula for the sum of the first n terms of the sequence is s of n. Find the largest positive value of the sum. Now that as a question by itself might not be very easy, but as a whole question here, we've been led through to this point. So we're going to use this part 2 here. A little bit of thinking tells us why. If we start at 30 and we're subtracting 1.5 each time, the first lot of numbers is going to be positive. We add those together to get the sum that's going to get bigger and bigger and bigger. But the amount we're adding is decreasing until eventually on the 21st term we add 0. And after that we start adding negative numbers and the sum will get smaller and smaller and smaller. So the largest positive value of the sum will be at this point here, where we start going from adding positive numbers before this to adding negative numbers after this. So I'm going to use r is equal to 21. That's where we add our 0, because everything after that will make the sum smaller. You could use r is equal to 20, because adding 0 itself doesn't make any difference. So I'm going to use n is equal to 21. We still know a is 30, d is minus 1.5, and we want to know what is the sum at term 21. 21 over 2, 2 times 30, plus n minus 1 is 20, times d is minus 1.5. If I stick all of that onto my calculator, I should get the correct answer. And I get 315. If you had lots of time to check this, you could do the sum of 20 terms and it should be the same answer. The sum of 19 and the sum of 22 terms should be slightly smaller than this, because this should be the largest positive value. Okay, that was arithmetic sequences, an exam question, and we talked about geometric sequences and series in the last video. Today we're going to continue geometric sequences and series, talking about the sum to infinity. So to get us going, let's go back to geometric series for a second. The sum of the first 20 terms. So remember, for geometric sequences and series, the sum of the first n terms is different. We've got a times r to the n minus 1 over r minus 1. Or there was an alternative, we could have a 1 minus r to the n divided by 1 minus r, depending on which one we wanted to use. So applying this, a was the first term, so it's 3. R is the common ratio, so 9 divided by 3, or 27 divided by 9, or 81 divided by 27 is also 3. And they want the first 20 terms. So we've got 3 times, I'm going to use the formula on the left, so 3 to the 20 minus 1 divided by 3 minus 1. And that is going to be a big number because of that 3 to the power of 20 minus 1 divided by 3 minus 1 is 2. That is, that's a big number, 5,230,176,600. Huge number. And the question we're asking in this video is, what happens to this sum if we keep adding terms, if we just keep going and add more and more terms? Well, in this case, this number is just going to keep getting bigger and bigger and bigger. It's not very helpful. There will be no end, it will just get bigger, bigger, bigger. And this is called a divergent series. And then we read it like this phrase in green here. Their sum tends to infinity. That means it just keeps getting bigger as the number of terms tends to infinity. So the more terms I add, the bigger the sum gets. This is true for all of arithmetic series and for some geometric series, but it's not true for all geometric series, and they're the ones that we're going to be interested in a few minutes' time. So let's have a look. Is this geometric series also divergent? Can go through the process again. We've got a is 2, r is minus 2 because the positives and negatives are oscillating, and we need just some number, let's use 20 again, and then we can look at a bigger number, 30 say, and 40, and see what happens. So the sum is 2 times a minus 2 to the power of 20 minus 1, all divided by 2 minus 1. So if I put that in here on my calculator, I get a very large number, but not as large as before, 2 million. Now if I increase that to n is 30, now I get a very big number, 2 billion. And if I go to n is 40, it just keeps getting bigger, 2 times 10 to the power 12. Very, very big. So yes, this sequence is also divergent. And that's not a surprise, I hope, because if this number here, the 20, the power, keeps getting bigger, then this term keeps getting bigger, and eventually this minus 1 doesn't really make much difference, and the multiply by 2 is just making it bigger as well. So as this power gets bigger, this answer will get bigger. Not a surprise. So how about this one? Let's go for white. Here we have our first term is 1, our common ratio is a half. Let's use the same one, n is equal to 20. And then I'll do 30 and 40. So just doing the same sum, put a 1 in here, and instead of a minus 2, we're going to have a half, and on the bottom, half minus 1 will be minus a half. And I get the answer. No, I don't. I haven't changed my power. 20. 1.999998093. So not a very big number, a little bit less than 2. And if I bring that power up to 30, 1.99999999998. And if I take it up to 40, my calculator runs out of space and it just tells me 2. So the sum here is not really very big. It's getting closer and closer to 2, but no matter how big I make my number of terms, I won't get above 2. This then, oops, sorry. This one is divergent, but this one is not divergent. Because although I can keep adding more and more terms, the terms are getting smaller and smaller and smaller. So as I add them, it's making less difference, and it doesn't just keep getting bigger forever to infinity, it starts to hit a limit. So if you're taking notes, a geometric series is divergent if its sum tends to infinity as the number of terms tends to infinity. And you can think of this graphically. This is the sum, and this is the number of terms. It's just going to go up forever. But it is called convergent if its sum tends to a limit as the number of terms tends to infinity. So this is kind of like having an asymptote. And it won't always look like this, but one of the options is it will look like this. And as the number of terms keeps getting bigger and bigger and bigger, the sum hits it a limit. So this, in our example previously, was 2, but it won't always be 2. And the key element that decides between these two is the common ratio. So if your common ratio is more than 1, or less than minus 1, if the magnitude is more than 1, then the power of that ratio, as the power gets bigger, the number keeps getting bigger. But if the common ratio is less than 1, then you've got a fraction, and as you increase the power on a fraction, the answer gets smaller and smaller and smaller, and eventually it gets so small you don't need to worry about it. And that's where we get this thing here, the sum to infinity. Now we do the sum to infinity of a convergent series only, because if it's a divergent series, you just get infinity. It's not very useful. But we've got a little formula here, and I'll fill this in a minute. That is the formula for the sum to infinity of a convergent geometric series. And I'll fill that in once I've gone through it down the side here. So we know the sum to n terms is this, or this. Now because we're looking at convergent series, and that is when the magnitude of r is less than 1, I'm going to choose this one here on the right, so that 1 minus something less than 1 will give us a positive answer on the bottom and a positive answer on the top, to avoid making any unnecessary mistakes with the negatives. But the key point here is this term. And as I said, if your r is less than 1, putting a big power on that is going to make this term, r to the n, really, really small. So we say as n tends to infinity, r to the n tends to 0. And in the limit, the sum to infinity, when n is equal to infinity, It's hard to do the maths there, but the concept is that r to the n will equal 0. And it will look like this. And of course 1 minus 0 is 1, and a times 1 is just a. So we have this slightly simpler formula. So the sum to infinity of a convergent geometric series is given by this formula, a over 1 minus r. Now it's very important we also tag on here that this is only true where the magnitude of r is less than 1. Okay, so that's the formula. That's the idea. Let's apply it to a few examples. Here we've got the fourth term of a geometric series is 1.08 and the seventh term is this. Show that this series is convergent. Now the key point here, if you need to show convergent or divergent, all you're looking for is this true? Is the magnitude of r less than 1? If it is, it must be convergent. If it is not, then it must be divergent. So we need to show that the magnitude of r is less than 1. To do that, we need to find out what is r. To do that, we need to use the information in the question. So we've got the fourth term. Remember, for a geometric series, the nth term is a r to the n minus 1. So the fourth term is a r4 minus 1 is 3 ar cubed. And that must equal 1.08. They tell us in the question. We can do the same thing with the seventh term. ar to the 7 minus 1 is 6. And that must equal 0.23328. And we've done this trick before. We can put these together by dividing them to find r and cancelling a. So ar to the 6 divided by ar cubed must be the same as 0.23328 divided by 1.08. So my a's cancel. I have r cubed is equal to 0.23328 divided by 1.08. And that is a very nice fraction because they are cube numbers. So r here is 3 over 5. Then we should put on the side here, magnitude of r is less than 1, therefore convergent. So the examiner knows you understand what that result means in relation to the question. Okay, part B. Now that we know it is convergent, we can find the sum to infinity of this series. To do that, we're going to use the formula we had on the previous page. And we know r, and we also need to find a. We can find a by putting r back into one of these two equations. So we know r cubed is this, so I'm going to put it back into here. So 8 times r cubed is 1.08, so 27 over 125a is 1.08, and if I do that quick calculation, I get another nice number, 5. So a is 5, r is 3 over 5. I can now find the sum to infinity. 5 over 1 minus 3 over 5, which is 2 over 5, so that's 25 over 2, or if you prefer your decimals, 12.5. Next example. For a geometric series with first term a and common ratio r, the sum to the first 4 terms is 15 and the sum to infinity is 16. Find the possible values of r. Okay, let me note the formulas again. For a, 1 minus r to the n over 1 minus r. and sum to infinity, a over 1 minus r. Okay, what I'm going to do here is a very similar idea, although using different formulas to the last question. I've got this information, so I'm just going to put that in here and get an equation. I've got this information, I'll put that in here, get a second equation, and then try to combine the two equations to find a and r. Specifically, r for the first part. So let's do this. The fourth term, s of 4, if I put n is equal to 4 in the equation, gives me 1 minus r to the 4 over 1 minus r. And that must equal 15 from the question. And then the sum to infinity is a over 1 minus r, and that must equal 16. Now this might not look very helpful initially, but if I just highlight in white here and here, we've got the same little expression, a divided by 1 minus r. And that's why I used this format of this formula rather than r minus 1. Although you could have made it work, it's a bit easier to see how these connect by using this formula. So I can substitute a over 1 minus r with 16, and I can do that here. So the formula on the left, or the equation on the left, becomes 16 times 1 minus r to the 4 must equal 15. And then I can rearrange this. So we've got 1 minus r to the 4 is 15 over 16. So 1 minus 15 over 16 is equal to r to the 4. I would work down the page if I had the space. And that is 1 over 16 equals r to the 4. Fourth root of that is 2, and it's a plus minus 1 over 2. So my two possible values of r are a half and minus a half. Part B. Given that all the terms in the series are positive, that means our ratio cannot be negative, so it's making it a little bit more specific now. If r is a half, find the value of a. Okay. So we had two possible values, now we've only got one possible value because all the terms must be positive. So r must equal a half, and we still know that the sum to infinity, which is a over 1 minus r, so that's a half now, that still equals 16 from the information in the question. But now we know what r half is, so I put that in there, and I can solve this to find a. 1 minus a half is a half. 16 times a half is 8. And there we go. So that is the sum to infinity. It can only be used on convergent geometric series. And if you've got a textbook, you can practice this idea using questions from exercise 5e. And maybe I'll see you in the next video.